Welcome to lesson 13. So we're going to talk about how we quantify the strength of linear relationships when we have two quantitative variables. So we do have that range of values where we said, hey, it's a very strong or perfect relationship all the way down to it's a very weak or there's little to no relationship. But we have a way of quantifying it. So we can measure how strong that linear relationship is between two quantitative variables with what we call the correlation coefficient, which the letter we use to designate it is the letter R. So here is that equation for the correlation coefficient. This is likely something that you calculated by hand in ST201. This is not typically something we expect you, especially not for an exam, to calculate by hand. This is something where you can use software, you can use a calculator. We don't expect these in general to be calculated by hand. It's a bit complicated for that. So yes, absolutely. The easiest way to get it is from software or calculator. So for this particular GPA example, so we're looking at high school GPA and first year college GPA. The correlation coefficient between high school GPA and college GPA is positive 0.82. So what does that even mean, right? So when we're looking at correlation is a number that goes anywhere from -1 all the way to +1. If it's equal to -1, it means that they are perfectly linear and it's a line that has a negative slope. If it's +1, it means they are exactly linear, so all the points fit exactly on a line, except it has a positive slope. If it's smack in the middle at 0, that means there's no linear relationship here. That or it's a exactly flat relationship. So if you have a positive value for R, so if it's between 0 and 1, that means that if you were to fit a line to the data, that line would have a positive trend. It would be increasing as you go from left to right. Conversely, if you have a negative correlation coefficient, that means that you have a negative association. So that as X increases, your Y is decreasing. So some more facts here. It's not a complete summary in and of itself. If you only use the correlation coefficient, you might be missing out on some very important information. So it's incredibly important to make sure that you have the scatter plot and that you look at the scatter plot so that you know that what the correlation coefficient in this context might mean. For example, all 4 of these scatter plots here have the same correlation coefficient. So if I just said, hey, I have a scatter plot that has a correlation coefficient of 0.7, it's not giving you a complete picture because none of these pictures look exactly the same or even roughly the same. I mean, if you look at this first photo, it looks like all the data is kind of clumped here and you have an outlier that's pulling the line up. If you look at this first one, it looks like a near perfect line, but this outlier is kind of goofing it up. It actually kind of pulls the line more smack in the middle. If you look at this third one here, you have 2 clusters. I'm not really sure that really would make me very happy. This fourth one is the one that I would actually feel pretty okay using the correlation coefficient with. I'm not seeing big old clusters. I'm not seeing really big outliers. That one I feel okay about. But so it's really important to know in and of itself, the correlation coefficient can't summarize the entire thing. You need to be able to describe that scatter plot. Things to know is because of the way that the equation is set up for the correlation coefficient, it does not have units. So if I had a scatter plot that was in feet and pounds and I converted it to centimeters and kilograms, the correlation coefficient is going to be exactly the same. It does not care about what your units are. It factors that out. So that's important to know. And a big thing, you don't want to use it unless you know that you have a linear relationship. So if you look at a scatter plot and you see any relationship besides a linear one, You should not use the correlation coefficient to describe the strength. That will be bad news. Further, you're going to need to have two quantitative variables. If you have anything besides two quantitative variables, your calculator is pretty much going to go, does not compute. It's not going to work. Because, well, one of them, you just can't do summations and whatnot when you don't have the number values. It doesn't make any distinction about which one's the explanatory and which one's the response. So if you're entering them in a calculator and you goof up the order, like you put X first and then Y, or you put Y first and then X, it will give you the same value. Although I really strongly recommend keeping it a habit to put them in the correct order, because it will matter down the road for the least squares regression line. So here's an example. Based on the scatter plot, which of the values here best estimate the correlation between the two variables? So first step for me, I like to just kind of estimate the line. I'm not saying that this is exact or anything, but looking here, it does look like, hey, I do have a somewhat strong linear relationship here. And not only that, as X increases, so does Y. So I should have a positive correlation coefficient. So right off the bat, I can say, well, it's not negative 0.7. It's not a negative value. So looking here, I would argue it's A or C, because none of the above doesn't really quite work here. So then you have to decide. So if it's 0.15, this would be a moderately or somewhat weak relationship. It would be, you look at it and you go, oh, maybe there's a line there. Maybe, but it would be kind of a stretch. If you looked at 0.85, you'd go, no, there's definitely a linear relationship here. It's not perfect, but it's fairly strong. Between those two options, I would go with A. 0.15 is far too weak here. And I know it's one of those, well, how do you know? I have been looking at these a while. And a lot of times, it's not like I can look at a graph and go, oh yeah, that's 0.85. It's more of, from these options, I could narrow it down. I have a lot of experience looking at them. Really, the best practice to figure these out is to get as much experience, just as much practice looking at these. Definitely the first step is going to always be, is it positive or negative? That usually will cancel out at least one of your answer options. And then you have to decide, is it really strong? Is it really weak? We don't usually give you answer options that are very close to each other. So that's worth noting. So one thing that most people have heard, even if they don't know what we mean by it, is correlation is not equal to causation. So just because two things are related to one another doesn't mean that one of them is causing the other, essentially. So just because you have a very strong correlation, don't be fooled, because unless we know that it's a well-designed experiment, so we know that we randomly assign treatments specifically, we can't say that one variable caused the other. We can't say that one variable caused the other to change at all. And the reason why are lurking variables. So these lurking variables, they can definitely come ruin the party, and they do. They do. They show up in plenty of studies. Actually, they fail to show up in some studies. So some examples of some headlines. So one was, studies show that women who own horses live 15 years longer. There's years in there, I'm pretty sure. Longer than those who don't. The implication from this headline is owning a horse causes women to live longer. And it's one of those, hey, should I run out and buy a horse? Will it help me live longer? Other than getting kicked out of my rental, I don't think so. Probably not. One working variable that's likely here is probably money. Money's a big one a lot of the time. So, women that can afford to buy and care for horses are more likely to also be able to afford healthcare. And women who can afford healthcare tend to live longer. This one's a fun one. I don't know why they decided to look at these two variables side by side, but did Nicolas Cage cause swimming pool drownings? So this particular one, Nicolas Cage, the number of roles he got in a specific year or whatever it was actually, fairly correlated with the number of deaths by falling in a pool. And I'm not really certain what the lurking variable or variables are in that scenario, but we probably should definitely question, like, do we really believe that, Nicolas Cage is causing these people to fall in pools and die? Probably not. Highly likely not. We're definitely not randomly assigning the number of roles he gets in a year, like every year. That would be really weird. So we are not doing that. And then do ice cream sales increase shark attacks? So that was found that as ice cream sales increased, so did the number of shark attacks. So did ice cream sales cause shark attacks to increase? Probably don't have to worry to the extent that you could probably go to the beach with ice cream and it's not going to cause a shark to come after you. But what a likely lurking variable here is weather, right? So warm, sunny weather. When it's warmer and sunnier, people tend to buy more ice cream. When it's warmer and sunnier, people tend to go to the beach more. The more people at the beach, the more likely it is there might be a shark attack. So here are just a small handful of examples where there's a headline here that definitely suggests that one variable is causing changes in another variable, and we really cannot say that that's true. So here's another example. We have a study that found countries that have more TV sets per capita. So if you even just look at per household, the more TVs each household has, the longer the life expectancies were in that country. So do we think that TVs cause longer life? So we think, oh, we need to run out and buy TVs. We're going to live longer. Well, I would probably, put my brakes on there. It's more likely related to money again. So TVs with more TV sets per capita tend to have more money, and countries with more money tend to have better health care and better life expectancy. Whether or not that's true everywhere, that's not proven. So working variable, the economic state of the country. So if they're a very prosperous country, they're probably going to have more TV sets. They're also probably going to have better health care. That'll increase your life expectancy right there. So some facts about lurking variables. So a lurking variable typically is associated with both of the other variables, so it can be related to your explanatory variable and your response variable. It tends to make it look like the explanatory variable causes the response variable to change, when that's not necessarily true. It could be impacting both of them, or it could be the one causing the difference. It's not like you can isolate just the explanatory and say it's just the explanatory doing this thing. So the lurking variable typically is what's causing the change in the response. And this is a variable that we typically don't account for. So we might know, oh yeah, we didn't, factor in weather with ice cream sales and shark attacks. But if we don't collect data on it, that makes it a working variable. So if it's not accounted for, if you don't actually measure or record it in the study, and it's something that's impacting the response variable, it's a working variable. Because even if you're aware that it's there, if you don't measure or record it, it's working still. It's just kind of goofing up everything. So that's going to be it for looking at correlation and working variables. Of course, we're always going to bring them up when we can, especially if it's amusing, like sharks and ice cream sales. We'll see you for lesson 14.